Welcome to another video. So in this video, we're going to talk about the even and odd identities of trigonometric functions, and we're going to talk about the Pythagorean identities stemming from the Pythagorean theorem of a right triangle as it is on a unit circle, inscribed on a unit circle. So let's get right into it. Now, if you never thought about even and odd functions before, this might be kind of new for you, but you should have seen them somewhere, but you might have never thought about trig functions as even or odd, and they are. So let's think about what even and odd actually mean. What even means is, if you think graphically, even means symmetric about the y-axis. That means, function-wise, that opposite inputs should give you equal outputs. That would create symmetry about the y-axis, and that's exactly what even means. Opposite inputs give you equal outputs. What odd means, graphically, is that you have this symmetry, but it's not about the y, it's not about the x, it's about the origin, which means you can take and rotate your graph 180 degrees, if you will, or pi, and you'd get exactly the same graph out. Here's what that means function-wise. Opposite inputs give you opposite outputs. Well, we're going to consider that, and hopefully you can see that that would create for you this symmetry about the origin. We're going to see whether sine and cosine do that. We're going to consider several different angles. Remember how sine and cosine and all these trig function works. Your inputs are angles. Your outputs are x or y coordinates. So it's a slight shift, and that's why I've shown you this here. Even means opposite inputs equal outputs. Your inputs, though, are angles. So your inputs here are opposite thetas equal outputs, f of theta, f of negative theta, those are outputs here. Well, the same thing happens with odd, but opposite inputs give you opposite outputs. Here's opposite inputs. Negative theta, positive theta, those are opposite inputs, are giving you opposite outputs. That is what odd does. This is what even does. Now let's consider these inputs on a unit circle. If I start taking a look at what's going on when my angles are opposite, remember that our inputs are angles. So let's take a look at what happens with my x coordinates and my y coordinates when my angles are opposite. All the way around a unit circle. One thing I want in your head right now is that x is cosine theta. Remember that. This is, well, x is mapped to cosine theta. Sine is y. And so when we take a look at this, let's look first at our x coordinates, our cosine thetas. Let's look at positive 30 degrees, negative 30 degrees, or positive pi over 6, negative pi over 6. Look at your x coordinates, they're in red. So that's square root of 3 over 2 and square root of 3 over 2. Wait a minute. We had opposite angles, one's positive, one's negative, counterclockwise and clockwise respectively. We had opposite angles, opposite inputs, and equal outputs. Does that continue? Here's pi over 4, negative pi over 4. Opposite inputs, opposite angles, are giving us equal outputs. Let's go to pi over 2 and negative pi over 2. Here's pi over 2, negative pi over 2. Opposite inputs, opposite angles, are giving us equal outputs. That continues. We can go all the way to 5 pi over 6 and negative 5 pi over 6. That's opposite inputs, opposite angles, giving us equal outputs for x, for cosine. So if we look at our x's, these opposite angles are always producing equal outputs. Opposite inputs are giving us equal outputs for x. So therefore, for cosine, cosine then, by definition, what even means is an even function. And so if we take cosine theta and cosine negative theta, opposites, they're going to be identical. That's exactly what this says. Cosine pi over 6, cosine negative pi over 6, you have identical outputs. That's great. Cosine is an even function. And that's what this says. Opposite inputs are giving you equal outputs. That's what that is. Here's what it means practically. If you see cosine of negative 30 degrees, it is equal to cosine of positive 30 degrees. You can just change the sign. Why? Magic. No, because they're even. And we just saw that on a unit circle. It makes some of our math really convenient to know that cosine is even. Graphically, it's important too. We're going to see that cosine does this about the y-axis. Now, what about secant? Because secant is the reciprocal of cosine, it's also an even function. So whether you plug in negative theta or positive theta to secant, you are going to get the same exact output. Opposite inputs equal outputs for even functions. Cosine and secant are your only two even functions. That means you can basically just change the sign of your angle and be right. This is also only true for, of course, where secant is defined. We have a couple places where it's not. 1 over x where x is 0. That would be pi over 2 and 3 pi over 2. So those two places are not defined anyway, and so of course this would not hold. Now what about odd? Let's look at our y coordinates. If I start taking, I'm going to go a little quicker here. If I start taking opposite inputs, opposite angles, our outputs for y are also opposite. So pi over 6, negative pi over 6, 1/2, negative 1/2. And that follows all the way around the unit circle. For opposite inputs, I'm getting opposite outputs for y. Therefore, for sine, because sine is y, what that means is that sine is an odd function. Opposite inputs are going to give me opposite outputs. That's going to create on our graph this function that's symmetric about the origin. It's going to look like this as we go through. No, it's not a cool dance move. It's exactly what sine does. So when we take a look at the definition of what an odd function is, by definition, sine is odd. Opposite inputs giving us opposite outputs. Well, therefore, if opposite inputs give us opposite outputs, then we can change the sign of our angle and it changes the sign of our function. That's what odd means. Because of that, cosecant is also odd. And when we compare them, when we have an odd function and an even function in ratio, when you have sine over cosine of theta in both cases, it's the oddness that prevails. So an odd function divided by an even function, every case I can think of, is going to give you an odd function out, and that's what happens with tangent as well. You can see it if you wanted to. Here is tangent of pi over 4 would be 1. Tangent of negative pi over 4 is negative 1. Those are opposite inputs, giving you an opposite output. So tangent's odd. Same thing for cotangent. So I've organized this for you. The only even functions you have are cosine and secant. For odd, you have sine, cosecant, and then tangent and cotangent. Those are odd. Here's what it means very quickly. It means that you can change the sign of the sign, positive or negative, of your angles, but you have to do it in relation to whether they're even or odd. Remember, cosine and secant are the only even ones. The rest of them are odd, and you change the sign of your function. Cosine and secant, you don't. So if I want to go down here to cosine of negative 30 degrees, cosine is even. Opposite inputs equal outputs. That means I could just write this as cosine of positive 30 degrees, and that's absolutely true. Now, is it any easier to find on a unit circle? Sometimes yes, sometimes no, but when we're dealing with identities, and a lot of times in calculus, and if we're dealing with inverses, you have to have it defined specifically, where your inputs can only be in a certain interval, and so this is very, very helpful for us. So if I have cosine of negative 30 degrees, I say, hey, opposite inputs have equal outputs. I can just change the sign and get the same output. Opposite inputs, same output. Then I know cosine 30 degrees is going to be the x, that's square root of 3 over 2. Now, I could have done cosine of negative 30 degrees, still square root of 3 over 2, but I'm showing this for you to practice so that when we get there, it's going to make sense. So this would be square root 3 over 2. Now, how about sine? Well, sine is not even, sine is odd. And so we can change the negative 60 degrees into a positive, but to do so, we've got to realize that opposite inputs are giving you opposite outputs for sine. So change the angle, change the sign of your function. That's what odds do. Even say change your angle, that's an input, don't change the sign of your function. So sine of negative 60, we certainly could have done sine of negative 60 degrees and got negative square root of 3 over 2. But now maybe it's a little bit nicer to do quadrant 1, a negative sine of 60 degrees. And here's how this works. You go to sine of 60 degrees. You say, okay, sine of 60 degrees is square root of 3 over 2. And this says make it negative. Yes, we get the same thing either way. But oftentimes, it's nice to be able to manipulate that angle to use in other identities. We'll see that after we talk about Pythagorean identities in just a little bit. How about cosecant of, or how, let's go secant. Secant of negative 30 degrees. If we did secant of negative 30, I need you to remember that cosine and secant are even. So secant of negative 30 degrees is the same thing as secant of positive 30 degrees. So what's that mean? Let's go to 30 degrees. Here's positive 30 or pi over 6. Secant says I'm going to take 1 over cosine. That is cosine. So I'm going to take 1 over cosine or reciprocate cosine. So cosine of 30 degrees is square root of 3 over 2. Secant, therefore, is 2 over square root of 3. If we rationalize the denominator, that's 2 square root 3 over 3. I hope it's making sense to you. I know I've thrown some degrees up there just so we can kind of refresh that those actually do happen as well. Most of the time we're going to use radians in this course, but we need to be used to both. How about cosecant of negative pi over 6? So we're thinking cosecant. The only two even ones that you don't change the function for when you change the sign of your angle are secant and cosine. Everything else you do. So cosecant is odd. We're going to change the sign of our angle. We're going to change the sign of our function. For those of you who have seen this before, I hope I make it easier. I hope that you're saying, oh, that's actually not that hard. If I just remember the evens, everything else is odd. I can just change the sign. That's fantastic. Okay, so cosecant of pi over 6. Let's think about this in terms of its reciprocal function. Cosecant in your head must be paired with sine. So I'm going to go to sine of pi over 6. Here's pi over 6. Here's sine. Now I'm thinking cosecant's the reciprocal of that. So again, I've said my angle, I'm going to think of positive pi over 6. I'm going to go to sine because that pairs up with cosecant. Sine is 1/2. Cosecant is 2 over 1, therefore. And then I'm going to say, oh, I want negative 2 over 1. I don't show a lot of work on these because I have in my head this process of how these things work together. And I've built that for you over the last several videos. So you can use it. That's okay. If you need to show more work, absolutely do it. But in most cases, when you get to it, it's not going to be that necessary for you. How about tangent of negative pi over 4? Because tangent is an odd function, I could certainly go down to tangent of negative pi over 4 and get negative 1. That's what we're going to get out of this. But to practice these odd identities and even identities, we're going to say tangent's odd. Why? Because it's not cosine and secant. Therefore, if I change the sign of my angle, I change the sign of my function. That's what odds do. So tangent of pi over 4 says, all right, here's pi over 4. Tangent would be y over x, that's 1. But this says, okay, this part would be 1, now make it negative. That's just negative 1. I hope that makes sense. That's where I'm going to leave you with even and odd as far as sine and cosine is concerned. So we understand, hopefully, that even, that's only cosine and secant. Odd is the rest of them, sine and cosecant, tangent and cotangent. So what we're going to do is come back with what the Pythagorean identities are. We'll practice in conjunction with even and odd. We'll put the two together and see what we can do. So let's take a look at the equation of a circle. Now, the equation of a circle, and it's missing something up there, is x squared plus y squared equals r squared in general. But on a unit circle, it's x squared plus y squared equals 1 squared, because the radius would be 1, or 1 squared is just 1. Now, this is quite interesting because we also know on a unit circle that cosine of theta is x. and sine of theta is y. So here's what we're about to do. We're going to say because cosine theta is x and because sine theta is y, we can substitute those into that equation of a circle. Why? Because we're talking about a unit circle here, and we're going to get what is called a Pythagorean identity. Why that is because it's based on the Pythagorean theorem, which is the equation of a circle, or the equation of how a right triangle described on a circle works, or any right triangle really. So what we're going to say is, if that's the equation of a circle, specifically the unit circle, because it has a radius of 1, then we know that on a unit circle, that's why we had to have that 1, on a unit circle, sine of theta is y and cosine theta is x. We understand that. What that means is we can make that substitution. So if x is cosine theta and y is sine theta, x squared plus y squared equals 1 can change into x squared plus y squared equals 1 squared, but 1 squared is 1. Now, we write powers of trig functions a little funny. We can write them in parentheses for sure, but we can also write it a different way. I need you to get very used to it. Where we can write that power is, well, we don't really want to just erase parentheses and do like cosine theta squared, because that looks like the angles being squared. Remember, all these trig functions have angles with them. That's very important to understand. We don't want to write that because we can square angles sometimes, but it doesn't, this is not what we are intending to do. We're trying to say the function itself, cosine theta, with the angle in the function, that value is being squared. The x value is being squared. How we write that is, instead of having the power 2 here, we actually put it here. That means cosine squared theta or cosine theta squared. These two things must become interchangeable in your head. Sine theta quantity squared is also written as sine squared theta. Also keep in mind that because of the commutativity of addition, you can write this differently. You can write this as sine squared theta plus cosine squared theta equals 1. That right there is called the Pythagorean identity for trigonometric functions, or at least 1/3 of them. Now there's some corollaries to it. Corollaries means follows directly from this. Things like this. Could you start like, hey, subtract cosine squared theta from both sides? Yeah, you really could. And this would be just like a corollary of the Pythagorean identities here. Now what's that mean to us? Well, later on, we're going to start using that. So if you ever needed to change sine squared into a cosine, you can do it. Or cosine squared into sine, you can do it. Or if you ever have sine squared plus cosine squared of the same angle, you can change that to 1. That's fantastic. That's what makes identities so valuable. A lot of students are like, I hate identities. You really shouldn't. I know they're difficult sometimes, but with those identities, they actually make your math way easier and sometimes even possible. Especially when we get to calculus, we deal with this stuff all the time. So what we're going to do now is I'm going to talk about 2 other Pythagorean identities that we can get. I'll show you the derivation of them, and then we're going to go through and practice them a little while. All right, let's take a look at the other Pythagorean identities that we can get along with their corollaries, which may or may not show up in your textbook. I don't know if you even are following one, but I want to show them to you here to make sure, at least 2 of them will, to make sure that you understand that there's lots of things we can do without actually having to look up angles and simplify some expressions. So I know I've written the same thing here. No, I'm not going crazy. I'm going to show you some other trigonometric identities that you can get with the Pythagorean identity that we started with. So what we should understand from what I showed you just a minute ago is that sine squared theta plus cosine squared theta, if your angle is the same, is going to equal 1. And we have some corollaries just by subtracting, respectively, cosine squared theta or sine squared theta. And we get, okay, a way to convert. Now, let's say that we did something else. Let's say that we took our original Pythagorean identity and divided all three of these terms by sine squared theta first, and then cosine squared theta for this one, and see what we get out of it. So if we divide both sides by sine squared theta, we're going to get not 0, we're going to get 1. We're going to get cosine theta over sine theta squared. Remember, this really is cosine theta squared, and this is sine theta squared. So we can kind of factor out factor out over division. Here, that exponent, we would get cosine theta over sine theta squared. But cosine theta over sine theta is cotangent theta. So this will become cotangent theta squared. We'd write that cotangent squared theta. Now what about 1 over sine squared theta? Well, 1 is the same as 1 squared. Sine squared theta is sine theta squared. So this we could think of it as 1 over sine theta quantity squared. But 1 over sine theta is cosecant theta. This, therefore, is cosecant theta squared. And we'd write that as cosecant squared theta. So by dividing all of our terms, or both sides, by sine squared theta, we get 1 cotangent squared and cosecant squared. That gives us another Pythagorean identity. 1 plus cotangent squared theta equals cosecant squared theta. And by doing the same exact thing we did here, by adding by subtracting some of these terms, we can also get, let's subtract 1. Cotangent squared theta equals cosecant squared theta minus 1. That's just subtracting 1. Or if we subtract cotangent squared from both sides, we'd get cosecant squared theta minus cotangent squared theta equals 1. So we can see those come up. These are mostly what you find, but the corollaries are very valuable, especially later on. Let's do one more. Let's divide everything by cosine squared theta. Well, if we do that, and for the same reasons here, we have sine squared theta over cosine squared theta. That's tangent squared theta. Sine over cosine is tangent. And so squaring that says, yes, you factor out the power 2 over division. And then sine theta over cosine theta is tangent. And we have tangent squared. Here we get 1, and here we get secant. Hopefully you see the secant. 1 over cosine is secant. And so we'd write that as tangent squared theta, 1, and then 1 over secant, so 1 over cosine squared theta is secant squared theta. That's our third and final Pythagorean identity. Now, let's write out a couple of these corollaries we can get. We could subtract 1 from both sides. We could subtract tangent squared from both sides and get a couple more. Namely, by subtracting 1, we can get tan squared theta equals secant squared theta minus 1, and by subtracting tangent squared theta, we can get secant squared theta minus tangent squared theta equals 1. And those come up quite often. Sometimes, if you're not shown these, you have to manipulate your original Pythagorean identity. It's not that hard, but the reason why I'm giving these to you is not to memorize them, but to understand that you can use them different ways, and that's very valuable. So let's start taking a look at some of these examples on simplifying. I know I've covered up some of them because I want to use the unit circle for this one, but I want to show you that we don't really need to for the rest of them. We're going to use our identities to simplify. But also I want to mention that I gave you a very basic way to start simplifying some of your angles that go more than one rotation around your unit circle. I'm going to start showing you a more advanced technique using the period of your trig function in which you're dealing and the remainder upon division of your denominator times that period. I'm going to explain that as we go on. It's a little more advanced. It deals with kind of a mod of numbers, a little bit of number theory in there on very much like how if you're familiar with measuring numbers, repeats every so often. Well, the same thing happens here because we have that repetition running in a circle. I'm going to show you what I mean by that as we get into it. So let's take a look at tangent. Tangent of negative 37 pi over 4. I don't like negative. I don't like dealing with negative angles. Let's change it. Because tangent is an odd function, we can write this as negative tangent 37 pi over 4. That's obviously a lot of times around the unit circle. How many? How many times, and then where would you end after you made those revolutions? Well, that almost is a division concept, isn't it? So I'm going to show you something kind of special. This is the way, it's a little bit more advanced of a way, but I want to start showing it to you. I've given you a basic way. I've given you the way, if you understand the period of tangent, that you can just subtract pi over and over and over and over again until you end on the unit circle. You can totally do that. So if you subtracted pi, you'd say, okay, that's 4 pi over 4. That's pi. The period of tangent is pi. Remember, the period of sine and cosine are 2 pi. So if you take this and just start subtracting pi, eventually you're going to get something on a unit circle. You have to do it several times. By understanding that process, here's what I like to do. I understand for tangent that the period is pi. I'm going to put 1 pi specifically. This is how I determine where this is going to lie. I take the period, that's 1 pi, multiply your denominator by that. Well, that's going to be 4. Remember that that's kind of like saying 4 pi over 4. And then what I'm going to do is I'm going to divide this number by that period times that number. Ultimately, you're taking 37 pi divided by 4 pi. Your pi's are going to cancel. You're going to get 37 over 4. That's how that works. 37 divided by 4. Now, I don't care how many times the 4 goes into that, because that's just going to be repetitions of pi around your circle. So I don't care how many times it goes into that. What I care about is the remainder. So 37 divided by 4. 4 goes into 37 9 times. That would be 36. It has a remainder of 1. So that would be subtracting 9 pi's, and you're going to get a remainder of 1 pi over 4. That works every time. Again, take this number, 37 pi, divide by denominator times period. The pi's are going to cancel. You're going to get 37 over 4 and look for the remainder. The remainder here is 1. That would be 1 pi over 4. Remember what you do with remainders. With remainders, when you divide, you take that remainder, you divide by what you divided by. That'd be remainder of 1 divided by 4. That was what you're dividing by. So can we find tangent pi over 4 easier than we can find tangent of negative 37 pi over 4? Yeah, way easier. Here's pi over 4. Tangent is 1. So y divided by x. And then make it negative. This is negative 1. Now, what would you do for sine or cosine? Well, the period's not 2 pi. Or sorry, not pi, it's 2 pi. So you take your numerator, like 37 pi, divide by 4 times 2 pi. That would be 8 pi. Pi's cancel. 37 divided by 8. Figure out how many times 8 goes into 37 without going over. That's 4 times. And then whatever your remainder is, you put that over your denominator. And then what you'd end up getting is something on the unit circle. So that does work. I hope that makes sense to you. What we're going to do now is we're going to talk about why we don't necessarily need to use a unit circle when dealing with some of these identities. So let's take a look at them. How about sine squared 40 degrees plus cosine squared 40 degrees? Now that looks oddly familiar because that is the Pythagorean identity there for sine and cosine. Sine squared plus cosine squared of the same angle always equals 1. I don't care what the angle is. There's no work to do here. There's no, I've got to look that up on the unit circle. No, you don't. No, that's why we have identities, to make it easier. Whenever you have sine squared plus cosine squared of the same angle, you are going to equal 1. What about secant squared 18 degrees minus tangent squared 18 degrees? Well, that doesn't look like that. No, it doesn't, but it's also the reason why I made sure to give you some corollaries here. So this could be manipulated back to tan squared plus 1 equals secant squared theta. You could do that, but check it out. Because I wrote down these corollaries here, I know that secant squared theta minus tangent squared theta, where your angle's the same, will also equal 1. Here's secant squared, tangent squared, minus, and the same angle. This equals 1. Does it matter that that's 18 degrees? Now, it could be 18, could be whatever, could be 19 degrees, could be pi over 4, whatever. This is always going to hold true for that. Now, how about things like this? When you have tangent pi over 4, sine pi over 4, cosine pi over 4, it might be very tempting to try to look these up. You're like, well, that's 1, that's square root 2 over 2, that's square root 2 over 2, square root 2 over 2 divided by square root 2 over 2 is 1, so 1 minus 1 is 0. That's true. But sometimes it's easier to use some of our identities to get there. For instance, do we remember that sine of an angle over cosine of the same angle, that is how tangent is defined. So this is tangent pi over 4 minus, that is tangent pi over 4. Sine over cosine make tangent with the same angle. This is tan. Now, while you certainly could have used the unit circle here, what if that wasn't pi over 4 but pi over 5? Well, then we can't do that. And so that's why we want to get very good at the identities. I hope you caught that. This is a very special angle, but if it wasn't on the unit circle, you would mightily struggle with this unless you had the identities. Now that we do, it says, I really don't even care what pi over 4 is. Tangent minus tangent of the same angle, you're subtracting the same thing. That's 0. Let's take a look at a couple more. So imagine we have secant of negative pi over 18, cosine 37 pi over 18. That's not in the unit circle. That's true. And that's why these identities are very important. So what we're going to do is try to make these as simple as possible. Some key thoughts. I'm trying to train you on how to deal with identities. Now, these are what are called basics. There's some basic identities. We're going to deal with ones that are much more hard, more difficult. But when you go through them, there's some key thoughts. Number 1, can we simplify the angles at all? Can we put those angles on a unit circle by using some of our basic identities like even, odd? Or if it's more than one revolution around the unit circle, can we translate that into an easier type of an angle? Then, after we do that, we try to get everything to sort of match up. If we have sines and cosines, put everything in sines and cosines. If we have tangent, try to put everything in tangent. Or try to make one of these identities that we're sort of building work. Even their corollaries, like we've seen before. So I'm going to start showing you that. Firstly, secant of negative pi over 18. I don't want to deal with the negative angle. So let's use the fact that secant is even and change it to secant of positive pi over 18. Now, I don't really like cosine 37 pi over 18 either, so that goes more than one revolution around that unit circle. We understand, hopefully, that the period of cosine is 2 pi. So, here's how I like to do this. Take your denominator, multiply it by your period. That's 36 pi. Take and divide them. So 37 pi divided by 36 pi. Pi's cancel. 37 divided by 36. 37 divided by 36. 36 goes into 37 one time. And has a remainder of 1. I don't care about that one. I care about that one. That remainder divided by that number will be exactly what this changes to after you subtract those revolutions. So this is going to be cosine of 1 pi over 18. Not 36, but 18 because the period's 2 pi, not 1 pi. Now that's true. Well, now take a look at this in a different lens. We've already simplified our angles as much as we can. They look really good and they're the same. That's great because then we can use other identities. So I don't want to look up pi over 18 on a unit circle. It's not there. So instead we think, okay, we have secant, we have cosine. If we have sines and cosines, write everything in terms of sines and cosines if you can. So here's cosine, here's secant. I'm going to write that in terms of sines and cosines. We know that secant is 1 over cosine. And because we have 1 over cosine times cosine of the same angle, since we simplified our angles, that equals 1. Okay, last one. So I've got sine negative 20 degrees, cosine 380 degrees, plus tangent of 20 degrees. Our first thought is simplify our angles. So I know that since sine is an odd function, sine of negative 20 degrees can be written as negative sine of positive 20 degrees. Change your angles sign, change your function's sign for odd functions. So I'm going to write this as negative sine 20 degrees. I have the cosine. That's more than one full revolution, 380 degrees. So let's subtract 360 degrees. So that's going to give us 20 degrees. Well, that's very convenient. Now we take a look at it. There's two options here. I know I just mentioned to you that you can write everything in terms of sine and cosine. You could write this as sine 20 degrees over cosine 20 degrees, and you could see that negative plus positive, the same thing, is going to give you 0. With tangents, a lot of times we want to see if we have other tangents somewhere in there. So in our case, we have sine divided by cosine. That is tangent of 20 degrees, but negative tangent of 20 degrees. And of course, negative tangent 20 degrees plus tangent 20 degrees, I don't care what tangent 20 degrees is, that's going to be 0. I hope that you've got a feel for how these identities start to work. We deal with a lot more of them, but this is just our jump off point. I hope I've made it very clear on how to, a slightly more advanced way, to change some of our angles into something simpler, something that's on a unit circle. I hope that you've understood everything we talked about in terms of Pythagorean identities. So next time we're going to go on to something a little bit different. For now, we should be practicing changing our angles into something on a unit circle and really getting a feel for how to use our even, odd, and Pythagorean identities. Have a great day.